Um, so we're gonna for this makeup class we're gonna talk about the topic which is not um, you know continuing what we did in class last week, but one extra topic that we need to cover at the end. So it's gonna be not quite related to the electricity or um, E&M stuff, but we need to cover it anyway. So I'm doing it here so that it doesn't break the flow of the class. Um, so it's about optics, and we need probably 2 lectures to complete that. So we have this lecture as a makeup, and then we have another one. So these two are gonna be the one that we use to talk about the optics. Okay. All right. So for optics, we talk about um, light wave mostly, but it's gonna be light wave where we don't really care too much about the wave property. So we're gonna assume a few things. So we're gonna assume that. So so we're gonna assume that um, light travels in a straight line. Okay, in reality, this is not 100% true because it can have some diffraction, something like that, but we will ignore that part. So we just say that light goes straight. And that's pretty much the only assumption that we're gonna make. And we're gonna talk about how, light change direction when it go into, different media or at the surface or something like that. So the first thing we're going to talk about is how light behave at the surface. And before we do that, we need to talk about one parameter which we use to characterize the medium, okay, which is anything that light travel in. And that's what we call the refractive index. Or sometimes called the index of refraction. It's the same thing. So this parameter n is a dimensionless number that we use to characterize how fast light travel in a medium, and it's defined to be c over v, where c is the speed of light in vacuum. Which is about 3 times 10 to the 8 meter per second. And then v here is the speed of light in any medium. So for example, if we have glass, the speed of light in glass is roughly about 2 times 10 to the 8 meter per second. Then we say the glass has the refractive index of c over v glass, which is 3 times 10 to the 8 meter per second, divided by 2 times 10 to the 8 meter per second, and that's about 1.5. Okay, so there are many types of glass, but the common kind of glass that we use to make like a cup or something like that is about 1.5 or 1.55, so about that number. So it means that light travel in glass slower than in vacuum. And normally we don't have vacuum, we're gonna have air, which is almost like vacuum in from the point of view of light wave. So for air, V is very close to C. So N of air, which strictly speaking is about 1.0003, but for most cases we're gonna say it's just 1, okay? Because we will not talk about that kind of precision in like in this context. So N of glass is 1.5, N of air is about 1. And then another thing that we probably need to know is water. Water has the index of about 1.3, 1.33, something like this. Okay. Of course, you don't need to memorize like these numbers, but it's a few numbers that it's probably good to know. But in the exam, these refractive index will be given anyway. All right. So because of the difference in wave speed or the speed of light in different medium, when light enters different medium, it will do two things. It will reflect and it will go through into the other medium. So if we draw an interface between the two medium, let's say we have air here at the top, and then we have water, and we have an interface between the two, should be horizontal. I'm trying to. That's strange. It used to automatically give me a horizontal line. Okay. So we have light coming in like this, let's say. This is the incident light, which is light that striking the interface. So this is called the incident beam. And the point where the incident beam hits the interface, we can draw a line which is perpendicular to the surface, like this. This is called the normal line. Normal in the sense of being perpendicular. And after this, there are two things that happen. First is the reflection. So for the reflection, it just bounces up like this. Okay. And then the other part is, let me write it down first. So this is reflection. And then the other part of light enters water, something like this. This is called refraction. And these three beams, we can characterize the direction by looking at the angle that is making with the normal line. So we can have this, we call theta I. So theta I is the incident angle, or the angle of incident. And then we have this theta R, which is the reflected angle. And then we have this one, we will call theta T, because we cannot use theta r that's already used for reflected angle. So theta t is the refracted angle, or t comes from transmitted light, the transmitted angle. Okay, three angles like this. And the relations between these angles, there's only, two kind of rules that we can prove it using electromagnetic wave theory, which we are not going to do in this class. So we just state the result, and it's the result that I think sometimes you probably know without thinking too much about it. The first one is that the angle of incident, the incident angle, is always the same as the reflected angle. So that means this angle is the same as this. And the second one is called Snell's law. This one relates the incident angle with the transmitted angle or the refracted angle. And again, this can be proved using electromagnetic theory. It says that if we have the first medium characterized by index of refraction n1, and then we have the light entering the other medium, which is characterized by n2, the refractive index, we're going to have n1 times sine of theta incident, theta I, or you can call it theta 1 if you want, equal to n2 times sine of theta 2 or theta t, like this. Okay, and if you know the angle of incidence and you know the refractive indices of the first medium, which is air in this case, and the second one, which is water, then you can calculate what is theta t, the refracted angle, using this formula. So for example, we have, let's say, from air into water, so we're going to have, let's say, the angle of incident given by this angle, let's say is 45 degrees air, and then going into water, which has more index of refraction. So in this case, you're going to low index to high index, and the light beam will refract towards the normal line here. Okay, if it's the other way around, let's say you're going from water to air, which is high index to low index, then it's gonna reflect out like this. Okay, but this is also captured in Snell's law. So let's say let's say we want to calculate what's the angle here, the refracted angle. So we have n air, n1 equal to 1, and then water we have, let's say, n2 equal to 1.3, okay, roughly speaking, and n1 times sine of 45 degrees equal to n2 times sine of theta t, okay, using Snell's law here. So n1 is 1, sine of 45 is 1 over square root of 2, n2 is 1.3, and then sine of theta t. So sine of theta t is 1 over 1.3 times 1 over square root of 2, and theta t is arc sine this number, and you will get about 33 degrees. Okay, so you can recheck with your own calculation. And you can see that 33 degrees here is less than 45. So you're going to have the light refracted towards the normal line. So if we have, this to be water, right, it behaves like this. Now let's say we flip from air to water and from water to air. Then we can reuse the Snell's law, but N1, N2 now kind of exchange, right, in terms of the definition. So let's say we have water, which is N1. Now we call N1, right, because that's where we start off. 1.3, and then we have air, which is N2 equal to 1. And the light, let's say, also come in with the angle of 45 degrees. So this is 45 degrees. Now in this case, because it's going from high index to low index, we know that it's going to reflect away from the normal line. So it's going to go this way. And we're going to use Snell's law to calculate this again. But in this case, N1 and N2 are different from what we had up there. In this case, N1 is 1.3. So we have N1 sine 45 degrees equal to N2 sine theta t. So it's 1.3 times 1 over root 2 equal to N2, which is 1, and sine theta t. So theta t is arc sine 1.3 divided by square root of 2, and this is going to give you 67 degrees. Okay, so the angle here is 67 degrees. You can see that it's larger than the incident angle. Okay, so this is something that you should at least know, that if it's going from high index to low index, that it's going to go away from the normal line. So because of this, you can imagine that if I increase the angle of incidence a little bit more, then the refracted light will also have more angle going like that. And eventually, if you have large enough angle of incidence, let's say you are going in with the red line like this, then maybe the refracted angle will be 90 degrees like this. Okay, that's possible from, like just from Snell's law, you can calculate where that happened. But light cannot really travel along the interface between the two media like this, because light is the oscillation of, electric field and magnetic field. And when it go across one medium to the other one, it will have to, like change some properties. So if you go along the interface, it has to, like go into water, go into air, go into water, and it just doesn't really happen in that case. So when the angle of the transmitted angle is 90 degrees, actually what happened is that you're not going to have any light coming out onto the other side. So where does the light go? Remember that we are talking about refraction here, but in reality we need to remember that there's reflection also happening like this. Okay, so in this case, there's no light going to the other part of the, the lower part, which is air in this case. So all the light will get reflected, 100%. This is what we call total internal reflection, and we can calculate where that happened. Okay, so that's going to be the next thing, which is again total internal reflection. So this happens when the refracted angle or transmitted angle theta t is larger or equal to 90 degrees from calculation, from Snell's law. Okay, so because it cannot really do that, right? 90 degrees, going along the interface, that's not going to happen. So going larger than 90 degrees, that's also pretty clear that it's not going to happen. So when this situation happens, then 100% of light will get reflected okay. So let's try to calculate when that happens. So let's take water to air interface again. So we have water and then we have air. And let's say we want to go into the interface such that the refracted angle or the transmitted angle is 90 degrees. So we want to go in here, and then we want the reflected angle to go like that. Okay, even though it doesn't really do this, but we need to calculate when this happens. And so when this start to happen, we call the incident angle the critical angle. So theta c is the what we call critical angle. Critical angle. So that means if incident angle is larger or equal to critical angle, then total internal reflection, which I will abbreviate with TIR, then TIR happens. So the critical angle is the angle of incidence that make refracted angle equal to 90 degrees. Okay, and critical angle will depend on what kind of media that you have, what pair of media that you have. So if we have water, which is N1 equal to 1.3, and air, which is 1, then we can try to calculate critical angle using Snell's law again. So we say N1 sine theta incident equal to N2 sine theta transmitted. So this is just stating Snell's law. So we can put in N1 equal to 1.3, and then theta I, the incident angle, we set it to critical angle, and that's when theta t is 90 degrees. So sine of 90 degrees is 1, N2 is 1, so we just have 1 on the right hand side. So theta t is then arc sine 1 over 1.3, which gives you about 50.2 degrees. Okay, so the critical angle for the water and air, pair of media is 50.2 degrees. So that means if you enter the interface with the angle 50.2 degrees or larger, then the only thing that happens is reflection. For example, if you have the interface like this, and if you go in with the angle of 60 degrees, this is larger than the critical angle, again I should say that it's still water and air set of media. So if larger than 50.2 degrees, then the only thing that happens is reflection. So all the light will reflect back like this. And you have nothing going into the other side. No reflection, no refraction at all, no transmission at all. Okay, so this is what happened. And you can see that if you try to calculate, the angle here, you get something strange. Because if you, let's say, want to use Snell's law to calculate theta t in this case, right? Let's try that. So it's n1 sine theta I equal to n2 sine theta t. Okay, Snell's law again. It's 1.3 times sine of 60 equal to n2, which is 1, right? That's air, sine of theta t. So theta t is arc sine of 1.3 times sine of 60 degrees, right? So if you use your calculator to calculate this, you will get that 1.3 times 60 degrees here. This one gives a value of 1.125. But sine of any angle cannot be greater than 1, right? The maximum is 1. That's when sine is, sine 90 degrees. But this is larger than 1. So this one will not give you any valid angle, right? So you're going to get an error when you use your calculator. So you cannot find the angle anyway. And this is another good way to check that you are in this, total internal reflection, case, because if you try to calculate the angle, you can't do that. Okay. Another thing that you can check yourself is that if we go from low n to high index high n, then TIR will never happen. So total internal reflection only happens when you go from high index to low index, like from water to air, right? If you go from air to water, then no matter what you do, the refracted angle will never be greater than 90 degrees. Okay. The extreme case is when you go in very close to 90 degrees here, but that will just make it look like that. So no reflection occurs. So if you want all the light to reflect back, then you need to make sure that the other side has lower index of refraction. Okay. So this TIR is what is used in the optical fiber. So optical fiber is just a really thin glass that is made into kind of like a tube, and when it's thin enough, actually we can bend it around. Okay, which is kind of hard to imagine because if we take glass, we try to bend it, it might just crack. But if it's made well, if it's thin enough, it can actually bend around, just like a cable. Okay, you can wrap it around, like anything you want, and that's exactly what's happening when you send, internet signal from one continent to another continent. So it's just, a tube of really thin glass, which is really long, hundreds of kilometers, and it's going around the globe, going underwater, it's what we call an intercontinental, fiber optic network, right? So we have like a house here, right? Maybe in Bangkok, Thailand, and then you can have somewhere, let's say in the U.S., right? So all the internet signal is routed through this optical fiber this way, and it's also going underwater, right? So um, without this, then there will be a very bad internet connection around the world, because nowadays we use a lot of bandwidth to send data from one continent to another continent. So essentially this is, optical fiber. And the way we send signal is nothing but you send light through this tube, and because this is glass and outside, you can think of outside being air, but it's not really like that. It's just a different type of glass which has lower index of refraction. But because total internal reflection happens all the time, so if you zoom in, then the light that enters this glass tube will just bounce around without leaving the tube, right? So you can carry light using this method, hundreds of kilometers. You might have the signal getting weaker as it goes along the tube, but you can have, what we call a signal repeater, which kind of make sure that you have, enough light signal to get through the whole cable. That's doable, but the amazing thing is that when total internal reflection occurs, like here, then really there's no light coming out onto the other side. So all the light, pretty much 100%, get contained within this fiber optical fiber. Okay, and that's the important application of this total internal reflection. So that's gonna be something that now you understand how it works. Okay, so that's the first topic that we talk about for today. The other topic we're gonna talk about is image formation for lenses, and it's a slightly long topic, so I think I will take a break here. All right, so let's come back in maybe 10 minutes. So 10:55 a.m. then we start again. All right, so we can take a 10-minute break. So, like I mentioned before the break, the next topic is, broadly speaking, is what we call image formation. Essentially, the topic about like how we see things. So normally when we see anything, we use our eyes, right? So to a very good approximation, our eye is just a spherical, ball of some liquid contained inside this ball, and we have kind of like biological glass at one entrance of the ball. So this is where what we call the iris of the eyes, so where lights enter, and we have kind of like a biological sensor, just like camera film of camera sensor, which is what we call retina at the back of our eyes here. And any object that we have, let's say we have like a tree. Okay, so when you have light strike the tree, that light might be coming from the sun or coming from a light bulb, then the part of the tree will give out light in every direction. Okay, so some of the light will go through the eyes, and the lens of the eyes will focus. We'll talk about that in a few moments, and put the light on the retina so that we can see the same picture of the tree here on the retina, and then our brain translate that into something that we understand. Okay, so if we take like the top part of the tree, okay, so light will go out everywhere. This exact same spot of the tree will give light in every direction, but part of the light will go to the eyes like that, and the other one like that. So the role of the eyes is to collect these light, and I'm drawing only two, but remember there's also a lot of them in between, so we are not drawing that. So these two are like the two extreme. So the iris, the iris is just the opening of the eyes. This is just like the lens of the eyes. We just you know collect light and then focus onto. This is a bad picture, so it looks something like this. Okay, so the top of the tree will appear here, and then you can repeat every other part of the tree. For example, the trunk of the tree, let's say, or the bottom of the tree. We also do the same thing. So we can have the light coming out from the bottom, and again there are two lights that we draw, and these two will get focused onto the other part of the retina, something like this. So we can see that by just simple like drawing of this picture, you expect the tree to be upside down on the retina, right? That's the image on the retina. And the reason why we don't see it upside down, because our brain like flip the image for us, right? So we don't need to like think about that. So everything is automatic, but this is what's really happening. So we want to understand how this works in this part of the lecture. Okay, so the first thing we're going to talk about is what we call a converging lens. Sometimes called convex lens. So what is this? Well, this one is a piece of glass which is curved. So it's not a flat piece of glass, it has to be curved. And because of the way light refract, because it's air outside and glass inside, right? The way it refract, we can show, which we not again gonna do a lot of proving that much here, but we can show that if you have a piece of glass shaped like this, which is called a convex lens or converging lens, its role is to converge light, right? That's why we call it converging lens. The role is to converge light, and then like put it onto one specific point. So if we have a light ray coming in from far away like this, or parallel, so going like this, okay, this converging lens will combine these light ray onto a single point, which is quite hard to draw if you have too many lines. But I hope you see what I'm trying to do here. Right, something like this, okay? So it will converge all the light onto a single point like this, okay? If you have light coming from far away, which is what we have here as parallel light ray. So this point here is called the focus or the focal point. And the distance from the lens to this focus is called the focal length, which is, the single most important number that we use to characterize lens. So it's gonna call this f. So f is the focal length. Right. So with only this one single number, then we pretty much know the property of the lens. So you're gonna say, okay, the focal length of the lens is, 20 centimeters, 30 centimeters, something like that. So this is light, this is parallel light ray, and parallel light ray is the light ray that coming from an object which is very, very far away, okay? But sometimes the object is not that far away. So how do we deal with that? And the goal of this whole thing is be able to, calculate the relation between two distances, the object distance and the image distance. So what I mean is that, let's say we have a converging lens like here, and let's draw the line, this line here. I'm going to do something like this. And the goal is to, calculate what happens if we place the object not at extremely far away, because that we know this is going to happen. But let's say we put an object at this location. This is the object. Can be anything, can be a car, can be a tree, can be a building. And the object is characterized by this distance, which we call S0 or SO, as in S of the object. So this is the object distance. Object distance. So it's going to be in, like 20 meters, 5 centimeters, something like that. That's the object distance. Light will go through the lens, and the lens will convert the light onto some location, which we might have the image upside down. And this is called SI, which is the image distance. And we want to know the relation between SO and SI. Okay, so that's kind of like the goal here. And again, the lens is characterized by one number, which is the focal length. Let's say focal length is 20 centimeters, right? So what's going to happen? Given SO, what is SI? That's the goal here. Okay, that's a very easy way of trying to figure out what's happening here. And the only thing that we need to know, well, two things. Well, maybe three, but I think two is enough. So the two things that we need to know is this. First, there's going to be a lot of light coming out from the object, right? Just like what we had up here for the tree. So the only thing that we need to figure out is where the tip of the object going to get projected for the image. And then the rest we can just draw it by hand. So the light ray coming out of the top of the object, the tip of the object, we have many, many directions. There are only two directions that we need to think about. First, the one that go through the center of the lens. That's going to be this one, going through the lens. So going through the center of the lens, because the way the lens is shaped, there's not going to be that much refraction happen when it's going through the lens. It will be some refraction, but very, very small. So to a very good approximation, going through the center of the lens will not change the direction of the light. Okay, so that's the first light ray, so we can draw it maybe something like this. So the first ray that you draw is the one going through the center of the lens, and just a straight line. The second light ray that you need is the one that goes parallel to the horizontal line. That means it's going to go like this. Okay. And this one is going parallel, so the way we draw it up here, all the parallel line of the light ray will get, converge onto the focus point, or the focal point, or the focus of the lens. So if the focus of the lens, let's say, is here, then we know that the top light ray here will have to go through this. So we can draw that line like this. Right. So make sure that it's going through the focus point. And where these two lines intersect on the right-hand side, that's going to be the tip of the image. So this is the only two light ray that you need to draw. And once we have that, that's going to be the location of the image. Okay. So let's try with the actual, example. So let's say we have a lens, converging lens, with focal length of, let's say, 20 centimeters. So we're going to draw a little bit more carefully here. So you all see, like this grid in my screen here. So we're going to call each grid to be 5 centimeters. So we can draw everything to scale. Okay, that's the plan here. So let's first draw the axis of the optical axis, which is just the horizontal line that we use to reference everything. So let's draw it like this. And I just learned that this is what you can do. And let's say we place a lens at the middle. Let's say we put it here. Okay. The focal length is 20 centimeters. That means there are 4 grids, right? Because each one is 5 centimeters. So 20 centimeters is 4 grids. So we can put a mark on the axis here. So this is the focal point, right? 1, 2, 3, 4 away from the lens. So each one is 5, so this is 20. You can also put it the other side if you want. Okay, something like this. And let's say we put an object at 30 centimeters away. Let's say we put an object SO at 30 centimeters away from the lens. So that's going to be 6 grid. So it's going to be here. This is our object. Okay, so 1, 2, 3, 4, 5, 6 grids away from the lens. So where the image gonna be, So we do, again, two lines. The first line is the one that goes through the center of the lens. So we can just draw it like this. And with the help of this new tool, I can do this. Okay, so that's the first line going through the center of the lens. Just a straight line because no refraction whatsoever through the center of the lens. The second line is the one that goes through the lens where it's coming in parallel. So it's going to be this. And then parallel light ray will get converged at the focal point. So the second part of this is going to be light that goes like this. So we need a little bit longer because they will have to intersect these two. Okay, so where they will intersect, you have to extend the line so that they intersect. So I have to do something like this, maybe like here. And then I extend also this line here. Okay, so you can see that the tip of the object get translated through the lens such that the tip of the image is roughly about here. Okay, so we can draw it there. So maybe something like here. So the tip of the object is there. So the whole object, the whole image of the object is going to be something like this. So that's it. That's how we draw this ray diagram. Okay, only two lines, one going through the center and the other one going parallel and then going through the focus point of the lens. Where they intersect, that's going to be the location of the image. So this is your image. And we're going to give kind of like special name for this image. We're going to call it real image. Because if you put a piece of paper here, exactly here, you will see the image of the object on the paper. Okay, that's where the light really intersect and then converge and then meet on this piece of paper. So if you put a piece of paper here, or you put your camera sensor here, you will see an image on the camera sensor or on the paper. We call this real image. In a moment, we're going to see that there's also a different kind of image which called the virtual image, where light does not really intersect and then meet at one point, but our eyes get fooled by thinking that the image is formed somewhere. But we're going to talk about in a few moments. But right now, let's check the distance of the image. So the image distance, SI. So SI in this case, let's count how far away do we have this from the lens. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So about 15.5 grids. And each grid is 5. So let's multiply by 5 centimeters. And you get about 77.5 centimeters. Okay, this is from drawing. So drawing is good enough to give you a rough, picture of the whole thing where the image is going to be. But if you want to really calculate what is SI, there's a formula that we can use. Okay, again, we are not going to prove this formula, but we can use it right away. And that formula is called the lens equation. Which is 1 over F equal to 1 over SI plus 1 over SO. Okay. The proof of this can be found in any textbook, any physics textbook that you have. So let's see if this agrees with the picture that we drew here. So 1 over F is 1 over 20 centimeters equal to 1 over SI, that's what we want to find, the image distance, plus 1 over SO, which is the object distance, 30 centimeters. So 1 over SI is 1 over 20 minus 1 over 30. So SI, by solving this, so I'm calculating that here, is about 60 centimeters. Okay. So you can see that from the calculation is 60, but the way we draw it is give 77.5. Right? So we drew it not quite accurate enough, and that's because a slight miss, drawing it badly, it can shift the image to be quite far away. Like for example, if you zoom in here, you're gonna see that my blue line does not start exactly the same place as the orange line. Right? So maybe if we change it a little bit, maybe like here, so you can see that it's gonna put the image closer, right? It's quite sensitive. So maybe this is not the actual location of the image. Maybe it's here. Right. So let's see if it's better. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right. So it's 12 grid times 5, and that happens to be roughly about 60, which is what we calculated here. Okay, so the drawing is good to give you a rough picture where the image is going to be, but if you want to know really where the image is going to be, then you need to calculate using the lens equation. But if you draw it carefully enough, then they should agree with each other. Okay, just like what I did here. Okay. If you want, you can add the third light ray that you want to draw. The reason why we put a focal point on the other side of the lens also, because you can also have light coming out, which is going through the focal point of the lens. I'm not sure if that's gonna be good enough here. Well, okay, the lens is not large enough, but let's assume that the lens is large enough. Let's say that's what we have here. Okay, and light coming from the focal length going through the lens will go out on the other side in a parallel way, and you can see that that's what's happening. So they also intersect at the same point. Okay, so you can see that we are drawing through 2 light ray or 3 light ray, but actually there's a lot of them that we are not drawing. So that means we're gonna have to think about what don't have to draw it. All other light ray that coming out here, and they are gonna all get focused onto the same point like this. Okay, but since they all get converged to the same point, then we only need 2 light ray or 3 light ray to be able to identify where this point is. Okay, and these two is usually the one that is easiest to draw and then good enough for any situation. Okay, so if you change the location of the object, let's say you change SO, then SI will also change accordingly. If you move SO close enough, you will see that SI using this equation becomes negative. So what's happening in that case? So let's try to do that. Okay, so we have the same length, which is f equal to 20 centimeters. But now we're going to put the object a little bit closer. So let's draw the optical axis first. Let's draw it like this, and then again put the lens somewhere at the center. Okay, and it's the same lens, so the focal point is 20 centimeters away from the lens. So that means the focal point will be here and then here. And we're going to put the object now at 10 centimeters, which is here. So SO is now 10 centimeters. F is still 20 centimeters. Okay, so let's see what do we have here. We're going to draw two lines again. The first line is the line going through the center. So that's going to be this line. Going through the center of the lens. And then the second line is the line that go parallel. And then get converged to the focal point of the lens, which is that dot that we have here. So you see that these two lines will probably never meet at any point on the right hand side of the lens, right here, because they are going away from each other. So there's no intersection anywhere. But if you put your eyes here, eyelash and then eyes, you're going to see something. Why? Because light, they are not intersecting, that's true, but from the point of view of your eyes, it looks like the light ray is coming from some other place. And what I mean is that the light ray, even though they are not intersecting, it looks like they are coming out from some imaginary object somewhere here. Our eyes cannot tell the difference. Our eyes thinks there's something here, the image here, which giving out the light, even though there's really nothing there, but our eyes think there's something there. This is called the virtual image as opposed to real image. Okay, as opposed to real image. And the reason why we call it virtual is because if you put a piece of paper here at the location of the virtual image, you're not going to see anything on the paper because there's no physical light that is converging and like focusing on that piece of paper. But if you talk about like how your eyes see things, your eyes only care about light coming into the eyes, and then it's gonna translate the image that you see. And you cannot tell the difference. Your eye cannot tell the difference whether there's real object there or not. Okay, so that's what we call the virtual image. And most of the thing that you see through the lens will be virtual image because that's what your eyes see. There's no actual image formation on this particular point. Okay, so from this picture, we can try to estimate where this virtual image gonna be. So we want to be a little bit more careful in drawing the line. So I actually want a dashed line, but I don't know how to do that. So we're gonna just extend this line to like here, and then extend this line to like here. And then where they intersect is the image. So the image is probably here. Okay, so remember the line that I extend here, that's supposed to be a dashed line, it's not the actual light ray. So by this drawing, then the distance of the image Si here will be 20 centimeters also. It happen to be the same as the focal length, but that's just some accident. Okay, so it can be any other things. And let's check from the length equation if this makes sense. So 1 over f equal to 1 over si plus 1 over so. Okay, so 1 over f is again 1 over 20. 1 over si, that's what we want to find. And 1 over so is 1 over 10. One over si is then 1 over 20 minus 1 over 10. And that gives you minus 1 over 20. So Si is minus 20 centimeters. So you can see that Si indeed gives you, 20 centimeters from the formula, and the picture also gives you 20 centimeters. But there's a minus sign, okay? So the minus sign is a very convenient way to remind ourselves that because it's a minus sign, is what we call the virtual image. It's not the real image. Okay, so the formula is very good in giving you the sign right away, whether it's virtual or whether it's real. All right, so we can summarize this formula by saying that if Si is larger than 0, then we have real image. And real image will be from a different side of the object. So if the object is on the left-hand side of the lens, the real image will be on the right-hand side of the lens. Okay, so S will be positive and the image will be upside down. That's the real image. If you have Si less than 0, then we call it virtual image. And the image will be on the same side as the object, just like what we had here. So the object is on the left-hand side. The virtual image is also on the left-hand side. And it's not upside down, it's upright for the virtual image, right? So these are the two things that you can remember and then remind yourself that this is going to be sometimes the case if you move the object closer. So if the object is somewhere between the focal point and the lens itself, then you will have a virtual image. Okay. The good thing about this is that you can see that the image is actually bigger than the object. And your eye is going to see that also, right? So this is a very good use of the lens to what we call magnify the object, right? So the object appears to be larger than what it is. And the magnification is just the size of the image divided by the size of the object. And it can be shown that it's actually just the ratio of the image distance to the object distance. And we put the absolute sign because for virtual image it's negative, right? So we care about the number, we don't care about the sign, so we put an absolute sign here. So in this case, minus 20 divided by 10. So the magnification of the system is 2. So the image will get will be 2 times larger than the actual object, right? So this is a very simple use of lens to converging lens to magnify objects so that you can see the details better. Okay. The other type of the lens, and that's going to be the last thing we talk about today, is called a diverging lens. Diverging lens or concave lens. And it's just the lens which is shaped in kind of like the opposite direction. So converging lens looks like this. So diverging lens will look like this. Okay, so this is diverging lens. And like the name suggests, the role of diverging lens is to diverge the light ray away from each other. So the way we define, in this case, the focal length or the focal point of this diverging lens is this. Okay, so let's say we have this optical axis and we have a diverging lens like here. Okay, so this is diverging lens. So diverging lens will make the light ray going away from each other. So if you have, let's say, parallel light ray coming in, one here, two here, three here, and then four here. Okay, so what happens is that this light ray will get diverged away from the center line, so it will go like this, like this, like this, and then like this. Okay, and if you extend this light ray back to a single point, they will virtually meet at one point, even though the light is not really converging there. But if you extend it back, they will meet at one point here. And this is the focal point of this diverging lens. And the focal length is the distance between the lens to this focal point. And because of this way that the light diverge away, the focal length of this diverging lens will be negative number. So let's say f is negative 20 or something like this. Okay, so the sign is also very important here because the sign of the focal length tells you whether it's converging lens or diverging lens. So if you have positive number, then it's converging. If you have negative number, then it's diverging. Okay, so okay, this is diverging lens. So how does it form the image? So we can do the same thing with the ray diagram. Okay, still you need only two lines. So let's do that. So let's say we have a situation where the lens has f equal to minus 20. So we know it's diverging lens. Let's say we have the lens here. Okay, and let's indicate the focal point. So there's going to be 4 grids away, and then it's going to be 4 grids away here. So that's our setup. And let's say we put an object at the distance here, which is 40 centimeters away from the lens. So SO is 40 centimeters. So that's 8 grids away from the lens. And let's see how we draw the ray diagram. The first one is, again, the one that goes through the center of the lens. That's easy, right? So we just start here and then go through the center. That's going to be our first line here. Right, going through the center of the lens will always just go straight. And then the other line is the one that goes parallel to the lens. And we know from the picture above that parallel light ray will get diverge away from the center. It's going to go something like that. Okay. But it's gonna go in a way such that if you extend the light ray back, it's gonna meet the focal point. So that's what we're gonna do for this particular line. Okay, so what I should do is I should just do it like this. Something like this. Okay, then I can go back here and then draw this dashed line. So that's the light going out, but you can see that the right hand side of the lens, those two lines will never intersect again. But if you put your eyes here, maybe a really big one, you're gonna see the light as if it's coming out from this tiny image here. So the object is here, the image is here, and this image is virtual image, right? Because no actual physical light ray intersect there. It's also on the same side of the object. It's also upright. So it meets every criteria of being a virtual image. So let's calculate using lens equation if this makes sense. So the lens equation for diverging lens works the same way as the converging lens, except you're gonna put focal length to be negative number. So 1 over f equal to 1 over SO plus 1 over SI. So 1 over f is 1 over minus 20, so it's minus 1 over 20 equal to 1 over 40 plus 1 over SI. So if you calculate this, then you get SI to be minus 13.3 centimeters. So 13.3 is about 3 something grid. It's not that accurate, but you can see that it gives a negative number, which is an indication of it being virtual image. Okay, and the location of the image, well, the drawing is not accurate, so you're probably gonna need to trust this number. But the sign here, negative, tells you that it's indeed a virtual image, just like what we expect up here. Okay, so in this case, if we calculate the magnification M, which is the absolute value of SI over SO, you're gonna see that it makes the object smaller. Right, it makes the object smaller, which is less than 1. So this one, it doesn't really magnify. It's kind of what we call like demagnifier because it makes things smaller. It might be a little bit strange to see like what the use of this, but sometimes you want to see more things. You don't care that it's smaller, right? This is the case where that might be the the application of this kind of lens. But the way that we draw the picture, the way that we use lens equation is exactly the same as the converging lens. Okay. The only thing different is the focal length. So I will summarize it here. So f less than 0 means it's diverging lens. F larger than 0 means it's converging lens. And then SO will always be greater than 0 because, there's no reason why SO can have to be negative. Because, some people say that if the object is on the other side of the lens, then we call it negative. But you can always flip the whole thing so that the object is always the left-hand side of the lens. So SO will always be positive, right? But SI is positive. We have real image, and SI less than 0 means we have virtual image. Okay, so this kind of summarize the sign of these variables S, O, Si, and then F, right? So if you follow this, then you're gonna have everything consistent with the way that we draw the picture here. Okay. So I think that's all I want to say for today lecture. And next time, I don't know when, next makeup, then we will talk about the last thing, which is the curved mirror, which actually use the same formula, but the interpretation is a little bit different. Okay, but in any case, well, thanks for showing up, two of you. Hopefully, there's still two of you, and I will see you on Monday, and then we will continue talking about electrical stuff in the lecture. Okay, so have fun with the open house. Then I will, see you on Monday. Goodbye then. Take care.